So we have seen that greedy search is doing a good job, but not always the best job. So for example, between Saint Louis and Sault Ste. Marie, we are not getting the shortest path to the goal. So another alternative to greedy search is to use the A-star search algorithm that actually will use not only the search heuristic, but also the cost to reach the node n. So to minimize the total estimated solution cost, we're going to combine what we call G of n, which is the cost to reach the node n. This cost actually is the real cost to go from the root to the node n. And starting from the node n, we want to be able to reach our destination or our goal. So we're going to use the heuristic that actually will give us an estimation of what would be the cost between n and the goal. So the idea of A star is simply to combine f of n, to combine g of n and h of n to get the function f of n, which will be used as the cost to conduct the search. So f of n is actually the estimated cost of the cheapest solution through the node n. So the algorithm is very similar to uniform cost search and greedy search, except for one detail, which is that now we are using a cost that is combining g of n and h of n. Otherwise, everything else remains unchanged. So let's see how A star works on our toy example of going from Saint Louis to Sault Ste. Marie. So in the initial state, we have Saint Louis. We start with Saint Louis. So far, we don't. The cost to reach Saint Louis is 0. So because we start, this is our initial state. So here, for now, we have a g of n equal to 0. Then from Saint Louis, so this will be the cheapest node so far. So we have 180, which actually represent the straight line distance between Saint Louis and Sault Ste. Marie. This is so if we have Sault Ste. Marie somewhere here, Sault Ste. Marie. The heuristic h that we have seen, the table tells us that a straight distance between for the node Saint Louis to reach Sault Ste. Marie is equal to 180. Okay, so combining g of n and h of n will give us a total of 180 kilometers. So the next step is after we explored Saint Louis, so we are going to put this node in orange to say that it is explored. We're going to explore the children of St. Louis, which will be Chicago, Kansas City, Little Rock, and Nashville. So note that the distance between St. Louis and Chicago is 104 kilometers, and the estimated distance between Chicago and Sault Ste. Marie is actually 107. So, so if we have Sault Ste. Marie here, St. Marie, so the distance here is 107. So this is actually g of Chicago, g of n. We are considering our n is here. G of n is equal to 104. H of n, the straight distance between Chicago and Sault Ste. Marie, is 107. So the total distance, which will be f of n, is actually 104 plus 107. So I'm going to have this estimation for each of the nodes in the fringe, and it turned out that Chicago is the one we should go with because it has the shortest distance, the shortest estimated cost using g of n and h of n. So next we're going to explore Chicago. Chicago has as children or as neighbors Duluth, Omaha, Pittsburgh. We're not putting St. Louis because it was already explored. We also have Kansas City that was already in the fringe, Little Rock, and Nashville. We do a similar job in doing g of n plus h of n, and we get the distances that are actually represented here. Next, we're going to explore Kansas City. We include in the fringe Denver, Oklahoma. We don't include St. Louis because it's already explored. We calculate the distance for Denver and Oklahoma as the real distance between St. Louis and Denver, plus the estimated distance between Denver and Sault Ste. Marie. So that's the idea. So the process will repeat itself. Among all the distances that we have between the cities that are in the fringe, we're going to pick Little Rock because it's the shortest. So we explore Little Rock. Same thing, we do so all these nodes are actually in the fringe. We're going to pick Nashville that has only 306 kilometer estimated cost to the goal. We explore Nashville. Now we do the same thing. The next one would be Pittsburgh. Pittsburgh expands into New York, Chicago, Washington, and Toronto, but we're not going to add Chicago because it's already explored. The shortest distance is Toronto, which is actually at 251 kilometer estimated from the goal. So we keep going. The children for Toronto are Montreal, Pittsburgh, and Sault Ste. Marie. Pittsburgh is not added because it was explored previously. the shortest distance among all the nodes that you see here in gray that are actually in the fringe is Sault Ste. Marie, that is 251 total cost, which means actually that this is actually g of n plus 0, because now the straight distance between Sault Ste. Marie and itself is 0. So g of n 251 is actually this path that you see here. Okay, so and we found our goal by going through this path, which would be actually the shortest path to the goal. So on the map, you will have this configuration where you start from Sault Ste. Louis. This is what we have been exploring. But then the distance in this case would be a distance of 104 to get to Chicago, plus 81 to get to Pittsburgh, plus 80 to get to Toronto, plus 90 to get to Sault Ste. Marie. So the total would be 255 kilometers, which should be actually the shortest possible distance between St. Louis and Sault Ste. Marie. So we found the optimal solution now using the A-star algorithm. If we do a similar process between Las Vegas and Calgary, we'll find a similar path to greedy search. So A-star always finds the optimal solution. Greedy search sometimes hits the best solution, but sometimes does not. So A-star does a pretty good job at finding the optimal solution. However, it must rely on a good heuristic, because a good heuristic can turn to be a powerful one that leads us to the optimal solution. So a good heuristic is known to be powerful if it has the property of being what we call admissible. So what is an admissible heuristic? It's a heuristic that never overestimates the cost to reach the goal. That is, it is optimistic. So it always has less than what it needs to reach the goal. So more formally, a heuristic is admissible if for all node n, the value of the heuristic at the node n is actually bounded by the true cost to reach the goal from the node n. So in the example of the map, we use the heuristic HSLD that actually is the straightest line between the two cities. And this heuristic is admissible because it's always less than the true cost to reach the node. So this is can be illustrated by this small example. So if we have two cities A and B, the straightest distance between the two cities is actually not a real configuration. It's just an estimation of the distance between A and B. However, if you use a true path between A and B through roads, you will end up with some path that actually links the two cities. But whatever distance you take, it's going to be bigger than the straight line distance between A and B. So this is an interesting feature of the straight line distance, that it's always less than the true real configuration of path between A and B. So how about the search criteria for A-star? The A-star is complete because if there is a solution, you will find it. Unfortunately, the time is still exponential and the space is still exponential, and the main reason is that it keeps all the nodes in memory to find the best possible solution or the optimal solution, which is the biggest problem. And you have seen in the previous example that actually lots of nodes were gray because they are all in the fringe waiting to be explored. So there is a big, an important use of memory to solve the problem. Finally, is it optimal? Yes, it is optimal. If there is a solution, it will find the best possible solution, which is a solution with the least cost in the search. So last note about heuristics. We have seen heuristics in the context of maps. Straight line distance turned out to be a good heuristics when you explore the map. In other contexts, you may need to find other kinds of heuristics. So let's take another example with the problem of the 8 puzzle, where you have a board and you need to move the tiles around to reach some goal state. So suppose we start with the start state and we want to reach this goal state. So the idea is to move the tiles around, up, down, left, and right until you put them, in this case, in increasing order. Okay, so the tiles are numbered between 1 and 8. So if you want to solve this specific puzzle, not all of them can be solvable, but if you want to solve this one, you will find the solution to go from start state to goal state in exactly 26 steps. Okay, so this is the true cost, the optimal cost to reach the goal state starting from the state. So possible heuristics could be, for example, using h1 of n, which is the number of misplaced tiles. So you look at the start state and you see how many of the tiles are not at the right place as compared to the goal state. So for example, 2 is not in its place. 4, none of them is actually in its final state. So the total distance, in this case, h1 of n will be equal to 8, which represents the number of misplaced tiles. Another possibility is to use what we call the Manhattan distance or the block distance. This is the sum of the horizontal and vertical distances. In other words, how many movements you need to do per tile to get to the right position. So it's called Manhattan because in Manhattan when we go from place A to place B, in general the indications are given in terms of blocks. You can walk 3 blocks to get to the point B. So this is a kind of a specific kind of counting distances. So this distance is simply the sum of the horizontal and vertical distance on the grid. So in this case, if we count the tiles 1 to 8, we are going to calculate h2 of n, in this case, for the start state, as actually the number of movements you need to do to move each tile to its final position. So if we start with tile 1, we're going to need to do 1, 2, 3 movements. So that's going to be 3 for the first tile. For the second tile, we need to move it to the right. It's going to be only 1 movement. So this is for the second one. For the third one, we're going to need to do 1, 2 movements to actually move the 3 to its final position 3, and so on and so forth. So the total distance in this case will be 18, which is also an underestimation of the number of steps of 26. So both H1 and H2 never overestimate the true cost to find the solution. I prefer H2 because it's closer as a number to the real total number of steps. Maybe this is too much of an underestimation, but both of them are admissible and will help solve the problem. So this was for heuristics. In other applications, you may need to find the combinations of heuristics and try to engineer that, but in all cases, as far as it is admissible, you'll be able to use it in A* and reach the optimal solution.